All right, welcome. Today, we're going to talk about one of the coolest, most famous algorithms in the entire quantum world. We're talking about searching for stuff, but not in the way you're used to. We're going to see how a quantum computer can find that one needle in a ginormous haystack, not by sifting through the hay, but by making the entire haystack scream, "The needle is right here." So yeah, let's get into it. So I want you to picture this. You've got this massive, totally unsorted database. We're talking billions, maybe trillions of entries. And you need to find just one specific thing. Classically, what do? Well, you pretty much have to start at the beginning and check every single one. It's slow, it's exhausting, and for the kind of datasets we have today, it's practically impossible. This whole thing is called the unstructured search problem, and it is a huge headache. And this slide just perfectly sums up the different ways of thinking about it. On the left, you've got your classic approach. It's a slow, steady, one-by-one march through the data. But on the right, that's the quantum way. See, thanks to this wild quantum idea called superposition, where a quantum bit can be both a 0, times, and a 1 at the same time, a quantum computer can basically look at everything all at once. It's not about being a faster searcher, it's about checking the entire database in a single go. So, how does this quantum magic actually work? I mean, it's gotta be more than just looking everywhere, right? It is. It's a really clever trick. Let's break down the beautiful algorithm that completely flips the script on how we find things. It's called Grover's algorithm, and if there's one word you need to remember, it's amplifies. See, this algorithm doesn't find the answer by looking for it. No, instead, it systematically boosts the probability of the right answer. It makes our target stand out more and more from all the wrong answers, until it's so loud and clear you just can't miss it. So, how much faster are we talking? Well, the speed up is what we call quadratic. Let's put that in real terms. If you have n items, a regular computer has to make, on average, about n divided by 2 checks. Grover's algorithm, it only needs to take about the square root of n steps. So for a million items, that's the difference between 500,000 steps and just 1,000. For a trillion items, it's 500 billion steps versus 1 million. The difference is it's absolutely astronomical. Okay, so to pull off this incredible trick, Grover's algorithm needs two key components that work together perfectly. Think of it like a recipe with two secret ingredients. Let's take a look at the secret sauce behind this whole thing: the oracle and the amplifier. First up, we have the oracle. Now this part is seriously clever. You build this oracle to know exactly what you're looking for, but when it finds it, it doesn't raise a flag and shout, "Hey, over here." Instead, it just quietly marks the correct item by flipping its phase. You can think of the phase as kind of like a hidden property. By flipping it, the oracle makes our target mathematically unique without actually telling us which one it is. It's like a spy that puts a secret tag on the target that only we know how to see. And that brings us to the second ingredient, the diffusion operator, or as I like to call it, the amplifier. Its job is simple. It takes that one item that the oracle just secretly marked and it boosts its signal. It basically takes a little bit of probability away from all the wrong answers and gives it to the right one. The analogy here of turning up the contrast on a photo is perfect. It just makes our target pop. So we have our marker, the oracle, and we have our signal booster, the amplifier. But the real magic is how these two work together. It's not a one-shot deal. It's this elegant, repeatable process, kind of like a quantum dance that step by step zeroes in on our answer. Let's walk through the choreography. Okay, so here's how the dance goes. First, step 1, we put everything into superposition. Every possible answer has the exact same, equal chance of being right. Then, step 2, we let the oracle do its thing and mark our target. Immediately after, step 3, the amplifier comes in and boosts that marked signal. And then we just repeat that two-step. Mark and amplify, a certain number of times. And when we're done, we take a look. We measure. Now, what's really cool is that for a small search space like the one we're going to see in this simulation, you don't even have to repeat the dance. You just do it one time. So what happens when we run through this process just a single time? All right, enough with the theory. What does this actually look like when you run the code? Let's get to the proof. This next slide is the actual result from a simulation. This is our quantum circuit's final report card. And boom, there it is. We were looking for the state 11. Now, before we started, every state 0, 0, 0, 1, 1, 0, and 11 all had a flat 25% chance. But after just one round of the oracle and the amplifier, just look at that. The probability of finding our target 11 has absolutely skyrocketed to over 90%. All the others are just noise. So let's be super clear. The algorithm didn't look at anything. It played a game of probabilities. It successfully found our item simply by making it the most likely thing to pop out when we finally open up the quantum box and take a measurement. It's a completely different and way more powerful way of searching. And listen, this isn't just some abstract science experiment. Think about the real world. Imagine you're an online retailer, and you need to find one customer who matches a super specific complex profile in a database with millions of people. Grover's algorithm could, in theory, nail that search way faster than any computer we have today.
Of course, before we get too ahead of ourselves, it's not a magic bullet, at least not yet. There are still some major hurdles. For one, building an oracle that knows how to find really complex things is incredibly hard. And today's quantum computers are still pretty noisy and error-prone, you know? That noise can mess up the whole delicate amplification dance. So scaling this up is a massive engineering challenge.
But here's the thing. Those are engineering challenges, not fundamental roadblocks. The theory works, the speedup is real, and it leaves you with this incredible question to think about. If quantum search is really this powerful, what kinds of problems that we think are impossible today, in things like drug discovery, or creating new materials, or even financial modeling, what will we finally be able to solve when the hardware is ready to run this at full scale?